Yes.
Okay. So, what subject you are being taught after school?
No, sir. I had extra classes from school after school.
Okay, extra classes. So, you have exams?
Yeah. No, sir. For to cover portions.
Oh, questions. Okay. So, where were we? Amna, have you tried out some questions? Acha, it's okay. However, you should do the questions now. Otherwise, you will, forget the process. Like you can get, confused. What is this SN1 reaction? What is SN2 reaction? What is a nucleophile? How it is attacking? How this racemization is happening? Amna, have you understood this thing? The formation of carbocation. I want to reply.
Yes, sir.
Have you understood this formation of carbocation in SN1 reaction? Any doubt? Because we have to cover our doubt first. Otherwise, we are stuck with the concepts, lot of concepts, but with no understanding. Mariam, where were you in last class?
Sir, I joined, but then later on I had some problem in my device, so I had to leave the class.
Okay. Okay. No issue. Let's begin the class. So, acha, we have completed this SN1 reaction. Okay. I was saying that you have to complete your homeworks. Otherwise, you will not understand the concepts. You have to understand the fully grasp the concept. You have to understand this. You have to do the homework. If you try it yourself now, then you will understand that how much you are understanding it. Okay. So you have to remember this. That SN1 reaction is dependent on the stability of carbocation. Till this we have done formation of carbocation. Okay. Then you have I have discussed with the students in last class that in SN1 reaction, racemization of this is called racemization because the product which is forming is 50% of the product has retained the structure and the 50% has the inverted one. Okay, let me show you with pens so that you can visually observe. Wait, let me get some pens. Mm. So am I visible to you?
Yes, sir.
Okay. See, in the screen you can see this carbocation which is sp2 hybridized, right? So sp2 hybridized means they will be present at 120 degree with it, like this, like this. Okay, 3 pens you can see at 120 degree angles. Okay, got it? So in one case, nucleophile is attacking from this side. Okay, so nucleophile, this black pen is a nucleophile. Okay, let's assume this has attacked on this carbon and this has been attacked like this. So it will be tetrahedral in structure. Can you see on the screen? Tetrahedral structure. Am I visible?
Yeah.
Okay. And the second case is that this will attack on bottom side. Okay. So they will rearrange it like this. They will get rearranged like this. Can you see this? They have been
Yes.
rearranged. Okay. In 109 degree to maintain a tetrahedral structure. Okay. Since this is sp3 hybridized. Got my point?
Yes.
So since 50% of the product has retained the structure like this one, and the 50% has been opposite. So overall, the optical activity of that solution will be 0. Okay, like if the first compound is rotating the, rotating the optical lights in 20 degree, other will be rotating like minus 20 degree. So overall, it will be the optical activity will be 0. So this is an optical inactive solution, and this is a racemic mixture. Okay. So are we good till here?
Yes.
So we will compare with SN1 later, SN2 later. So in SN1 reaction, racemization of mixture, or you can say solution, took place. Express. Okay. Do you people understand chirality? Chiral?
Yes.
So, so chiral carbon, they show optical, they are optically active. However, the whole solution will be optically inactive. Individually, they are optically active, but since they have their counterpart present in the solution, that is why, the whole solution will be optically inactive. Okay. Any doubt?
No, sir.
Okay. So good. Now we will move to, we have completed this SN1 reaction. We'll move to SN2 reaction. SN2. So SN2 refers to bimolecular nucleophilic substitution. By first point, it refers to bimolecular nucleophilic substitution. So, that is why this 2 is coming from here. This 2 is because of this bimolecular. That is why. And SN1 is unimolecular. SN1 is unimolecular. As we have seen, this rate depends on only one molecule, and here rate depends on nucleophile as well as substrate. Okay, that is why this is bimolecular. Bimolecular, that is why SN2. This is unimolecular, only dependent on substrate. That is why SN1. Okay, understood?
Yes, sir.
Is this your first class? or you have done some classes earlier? I'm asking everybody. Sufyan,
Yes.
is it your first class?
First lesson.
Hmm?
No.
I'm not talking about a school.
Mm. No, it's not.
Okay, which class you have done earlier?
No.
Hmm?
Yeah.
Why I cannot feel energy in your people? So rate depends on both haloalkane and nucleophile. That is why this is known as SN2 reaction. The next point, rate is proportional to the concentration. This is the symbol of the square bracket, means concentration of nucleophile or concentration of any compound, and concentration of this Rx haloalkane. Okay. So rate is proportional to this. We can say rate is equal to K times nucleophile. Thus, this is the SN2 reaction. Bimolecular reaction. Acha, you know the order is the sum of power of the concentrations. Do you know this from the chemical kinetics? Have you studied chemical kinetics yet?
No, sir.
Okay, okay, no problem, no problem. Sorry, sorry. So the here there is one present here, there is one present here. So 1 plus 1 is equal to 2. The order is the summation of the power of the concentration of the concentration of the this which concentration of uh, the product on which rate is depending. The order is 2. You need to remember this. No problem. We will discuss in later chapters. And molecularity is molecularity. Since two molecules are involved in the rate, so molecularity is 2. Okay. Got it, people?
Okay. Yes, sir.
Good. So till here, we have understood the what is the basic definition of SN2. Let's go through the mechanism, and this is very important. And also, we will compare it with SN1 reaction, and then your all doubts will be clear, because what is actually happening. We will go through the mechanism. So what is happening? First, we will write it down. In meantime, you write this para above. Just let me know if you are having some doubt with any statement. I can repeat, or make you understand with another ways. Can you write these down first? Done?
Yes.
Everybody?
Yes, sir.
Okay. So let's see what is happening. Let's go through the mechanism. So C is bonded with a halogen, okay, and there are other components. Let's assume it 1, 2, 3. It can be H. It can be any alkyl group also. CH3 can be attached also. C2H5 can be attached, or hydrogen can be simply hydrogen is attached. Okay, and what is happening? What is happening? That nucleophile is attacking from behind. Okay, nucleophile is attacking from this side. Nucleophile is attacking. Okay. It would be better if I drop that. That would be more appropriate. Nucleophile is attacking on this carbon. Acha, do you remember this X halogen? Halogen has very high electronegativity. So here we will have partial negative charge or partial positive charge on this X.
Negative.
Negative charge, right? Good. So since this is electronegative, it has gained some partial negative charge. And in this carbon, we have some partial positive charge. So obviously the nucleophile, the nucleus level, the positive level thing, this electron rich thing will attack on this carbon, right? Obviously. Okay. Are you there?
Okay.
So what will happen in this, in the intermediate thing? What is happening? This nucleophile is being attached with carbon. Nucleophile is being attached with carbon, and this halogen bond is being broken. Halogen bond is being broken. So this is bond formation. This is bond formation. This is bond formation, and this is bond dissociation. Okay, so simultaneously this both thing is happening simultaneously. Okay, are you getting this?
Yes, sir.
What will happen finally? This this nucleophile will go out of the picture, and nucleophile will come into the picture and has made bond with this carbon, and had made bond with this carbon. So this will be obviously a sp3 carbon. So tetrahedral structure will be present, right?
Yes.
So initially also we have a tetrahedral sp3 carbon, and finally we are also getting sp3 hybridized carbon. Thus we have 109 degree with each other. Okay, and there is a clear indication. Kindly observe, there is a clear indication that this molecule has been inverted. So inversion has been taken place. Inversion took place here. Can you see? Inversion of molecule. Is it clear to you?
Yes, sir.
Amna,
Yes, sir.
is it clear that we have seen 100% in 100% inversion? You can tell it now, no problem. Amna. Mariam.
Sir, your voice is breaking.
Oh, sorry. Mariam, have you understood the concept? Mariam. Sufyan. Taha.
Yes.
Yes, sir.
Is it okay for you?
Yes.
Yes.
Okay. Okay. So in the square bracket, what we show in the square bracket is the transition state. So this is not, this is not visible in the compound. However, this is a short time period. This compound is formed. As you can see, carbon is holding 5 atoms with it. So this is very short period transition state formation of a compound. Okay, and finally we have got 100% inverted compound. Okay, kindly note this down. Done.
Yes, sir.
Yes, sir.
Okay, so we will write some points. I hope you have understood these problems. This concept. Everyone.
Yes.
Amna.
Yes, sir.
You have understood the concept. Let me
Yes.
know. Okay. So now we will, proceed to the next point. Factors affecting. Like both are very similar, na SN1, SN2. That nucleophilic substitution is happening here In the first case, just remember the formation of carbocation is taking place and racemization of mixture is taking place, means inverted product is also forming, and the retention product is also forming. But in SN2, the whole product is different. It has been inverted, 100% inversion took place. So factors first will be nature of substrate. Substrate, you people understand this? What is substrate? Anyone?
Yes, sir.
What is a substrate?
Organic compound.
You can give example also.
RX.
Rx, yes. So the actual organic compound in which we are working, we are doing experiments along, that is a substrate. Okay, good. So here in haloalkanes, substrate will be always Rx. Simple. So we will deal with these things in which we will deal with what is the nature of substrate and which will promote SN1 or SN2, and the nature of leaving group also, and the effect of solvent. Okay, so in which this reaction is taking place, nature of solvent. Okay, so first is nature of substrate. In the nature of substrate, we will see reactivity of SN1. So in this, we will compare that which will be having more faster SN1 reaction and which will have much slower SN1 reaction. So the important points which we have to note. So in this topic, we will revise, nearly each and every point of SN1 also. C plus is carbocation. I hope you people understand this.
Yes.
Have you been taught the rearrangement of carbocation?
No, sir.
Huh? Yes or no?
No.
Okay. From the statement, as SN1 occurs via intermediate carbocation, the reactivity depends on the stability of carbocation. Obviously, if we have a stable intermediate, the reaction will occur very easily, very soon, right? So this is very important point. That rate of SN1 is dependent directly on stability of carbocation. So now this GOC comes into play. You have to remember or try to remember, like for example, a rate of SN1. Can anybody, comment on it that 3-degree carbocation is more stable, or 2-degree carbocation is more stable, or 1-degree carbocation is more stable? 3-degree carbon, right? So 3-degree carbocation is more stable than 2-degree carbocation than 1-degree carbocation. Okay. Then if there is some resonance, right? Wait, let me check what I okay. So if there is resonance, the carbocation stability will increase to multifolds, right? Hello.
Yes, sir.
Are you there?
Yeah.
I cannot hear you guys. So like this, if we will compare, like for example, if we compare this, which is more stable? Kindly comment. Which carbocation is more stable? First, second, or third? And which one is the least stable?
First is most
Sir,
stable.
tertiary.
Hmm?
Sir, third one is more stable.
Third one is more stable.
Yes, and
Then
primary is
Then-
least stable.
then first or second?
Sir, first is least stable.
First is least stable. Okay. Any other answers?
First is most stable.
First is more stable. Okay, we have two different answers. Can you? I think Sufyan and Taha has answered, right?
Yes.
Sir, I'm first from the right.
Okay. Amna and Mariam. Mariam audio is having some problem. You can message also. Amna, what do you think? Hello. Amna. If you're not getting this, you can ask. Otherwise, slowly we will finish the chapter and you will have problem that with the stability of carbocation. So the right answer is the first one is most stable, okay, and the second one and the third one. How? Let me tell you. So Sufyan, you were right. So you were with the correct answer, right? Or Taha, you were correct. Who was correct?
That's correct.
Okay. So no problem. See, this is in the first one. You can see this positive charge has been distributed, with these much carbon at alternate carbon, at the alternate positions. This positive charges being distributed, and in this one, due to resonance, this carbon and this carbon is having positive charge. Okay, and in this position, this in this product, only this carbon has taken this partial positive charge. So as you can see, this positive thing, the positive charge means in instability, right? I've already told you that neutral species are always stable than cation or anion in each and every case. Got my point?
Yes, sir.
So this positive charge means lack of electron in it. So here this lack of electron has been distributed with 4 carbons, and here lack of electron has been distributed with 3 carbons, and here only with 2. So it is quite understandable that each and every carbon will have lesser share of lesser share of positive charge on it, right? Taha, have you understood the concept?
Yes, sir.
Okay, so try to remember this. Then for example, wait. So till here we have understood the problem. Let's check with another examples. You have to understand this one. This may be new to you, but this is very popular thing. This we have this. So can you tell me which one is more stable? Which carbocation is more stable?
First.
Okay, then
The third.
third, then second, okay. Taha, what do you think? Taha,
Yes, sir.
what is your answer?
Sir, I think it's the first one.
First, then
Then second and third. I mean, no,
Then
third
third.
and second.
Third, and then second. See, the right answer is, it could be shocking to you, but I'm here to explain it. The second is the most stable one here, then the third one, then the first one. Okay. So see, what is happening? This positive charge, na, this is a special case. This is called, dancing resonance. Dancing resonance. Resonance. Or it can be said sigma bond resonance. This is a special case in which this happens with only this one. It is not possible for this. Let me tell you. Otherwise, you can think that, oh, every time this is possible. This is not for this butyl thing, cyclobutyl. Only for cyclopropyl. Okay. This is special case. Got my point? So this one is very much
Yes.
stable. Actually, you know pi bond takes place in resonance, right?
Yes, sir.
When there is pi bond, you can understand that yes, there is resonance happening if there are in conjugate position. However, in conjugate position means like alternate position, like C. In this one, alternate position. In this one, the real diagram of benzene at alternate position, right?
Yes.
So what I was saying, that in this actually sigma bond is resonating. So this is known as sigma bond. This is a sigma bond, right? Carbon carbon bond is a sigma bond. This is taking part in resonance. That is why it is very much stable. Okay. So second one is a highly stable thing. It is more stable than this benzene rings. Okay. Now let's compare the. You have already understood that at conjugate position or at alternate positions we have positive charge. In this one, this excellent 1, 2, 3, 4, 5. Oh, there is 6-member thing. I'm really sorry here. One, two, three, four, five, six. Okay. See, this positive charge will be shared by two benzene rings. So we will have delta positive here, as well as delta positive. Since this is symmetrical, so this positive charge will be, taken in by this resonating structure also. So we will have how many carbon this positive charge have been shared? This 3, 3, 6 and 7. 7 carbon are, have distributed this positive charge. And here we have only 4 carbons which the positive charge has been distributed, right? So this is the correct answer. Okay.
Yes.
So got my point?
Yes.
Everyone? Let's make one. So resonance is clear to you, right? Is resonance clear to you?
Yes.
Okay. Now I'm just revising your concept of hyperconjugation. So we have positive charge in this one. We have also positive charge with this one. Just taking 3 examples. Can anybody comment on it that which one will be the more stable one? Which carbocation will be the most stable one? This carbocation, or this carbocation?
First.
So okay, Amna and Mariam, I'm not getting any response from you. Are you still there in class, or you just just
Yes, sir.
so you are here? Have you understood all the concepts we have dealt above?
Yes, sir.
Okay. So, what we were discussing. Which carbocation is more stable? This carbocation, or this carbocation? So, thus, yes, the first carbocation is more stable, then second, then third. Why? Let's discuss also that we have, this is known as alpha carbon. Have I do you know this? This is the carbocation, which is the carbon which is having positive charge on it. This is called alpha carbon, and the rest which are directly joined with the alpha carbon is known as beta carbon. Is known as beta carbon. Do you know this?
Yes, sir.
Okay. So this is also alpha carbon. This is alpha carbon. So uh, in this in this one, sorry, when carbocation is there, the alpha is denoted as the carbon, just the carbon which is directly attached to the carbocation. So this is alpha carbon. Okay, this is alpha carbon, this is alpha carbon, this is alpha carbon. Okay, so actually we have to count alpha hydrogen. Hydrogen directly attached with the alpha carbon is alpha hydrogen. Okay, alpha hydrogen. We have alpha hydrogen. So how many alpha hydrogen can you see? Can you count and tell me how many alpha hydrogen are present here?
0.
This one is carbocation. Okay, this is I'm sorry, this is alpha carbon, this is alpha carbon, and this is alpha carbon, and these are alpha hydrogens. These are alpha hydrogens. Okay, these are alpha hydrogens. So how many alpha hydrogen can you see? 3, 3, 3.
9.
9 alpha hydrogen. Here, how many alpha hydrogens can you see?
6.
6. And in this one?
3.
3. And let me draw one more structure that will complete your this carbocation thing. So we have how many alpha hydrogen in this last one? How many alpha hydrogen present here?
None.
Alpha, none, 0, right? So the more the alpha hydrogen, more will be the stability. Okay, more the alpha hydrogen, more will be the stability. Okay, I hope you understand this point, everyone.
Yes, sir.
Good. Kindly note this down. Have you noted till here? This one, the blue one, rate of SN1 proportional to stability of carbocation. Hello. Yeah, you have to note it from this one, the activity of SN1. Sufyan,
Yes.
what is? Amna,
Yes, sir.
noted?
Yes.
Okay, note this down. Done. Sufyan, Taha, Amna, Mariam. Neither you people are turning on cameras or
Yes, sir.
speaking anything. If you will not respond in the class, means you have to turn on your camera. Sufyan, have you noted?
Yes, sir.
Amna?
Yes, sir.
Okay. Okay. So now let's see this unique example. What do you think? This is stable or unstable? This one, which I have drawn. From your knowledge,
Unstable.
unstable. Why? Your answer is correct. It is actually very unstable. Why?
There's no resonance.
Hmm.
And only 3 alpha hydrogen.
Ah,
Only 2 alpha hydrogen.
no. Acha, it cannot resonate. What you are saying? Hello. Can you repeat?
Yes. There's no resonance.
There is no resonance. You are partially correct. Yes, there is no resonance. And the main reason, because this double bond, na, CH2, CH2, this has high electronegativity. Has high electronegativity. Okay. So if, and this one also, this CH triple bond CH, its electronegativity is around 3.5. Its electronegativity is around 2.8. So its electronegativity is very high. Like chlorine is having positive charge on it. It will never like positive charge on it. It is electron deficient. So how a positive charge is possible or stable on an electronegative compound or substance. So this is very unstable. Okay, got my point?
Yes, sir.
Yeah. Good. So now let's do some questions. These questions are from NCERT. This thing which I have taught now, this one, that particular, this is very important. It will always, you have to know this every time in this organic chemistry. Means you cannot afford to forget this. These things that, okay, this positive charge is taking part in resonance. This positive charge has been distributed. Okay, if there will be negative, then this negative charge will be distributed. Okay, this is more stable than this, than this. This is a special case. exception, and this is less stable than this, because here two benzyl rings are covering this cation, or if it will be anion, then also means more charge distribution, more stability. Okay, and this resonance thing is, sorry, hyperconjugation, counting of alpha hydrogen. Okay, these are very important things, and this also very unstable thing. So these will come in in each and every chapter. So predict the reactivity of 4 ice. Okay. So bromobutane, this is a butane, right? Everybody. And what is the other isomer we can make from this of a butane? This one. This is also butane, right? We have 4 carbons available here. So four carbon is there is a 3 carbon chain, but we have we have to deal with the 4 isomeric bromobutanes. So we will attach bromine here, then we will get bromobutane. So the structure we will get, there are 2 possible structure in isomers. Also you may have studied this, but we will deal with it like this. This is a also a bromobutane, and this is also a bromobutane, right? Got my point? Are we
Yes.
good? Okay. And this one we will have also 2 structures. One we will put bromine here in this one, this carbon, and other where we shall put it. Can anybody comment? First one we have attached bromine with this carbon. Shall we connect with this carbon, bromine, or this carbon? Will not the product will be the same one, since the structure is symmetrical, right? If we will attach bromine here, then
Yes.
also we will get this.
Yes.
If we will attach bromine here, then also we will get this, right? So where we shall attach bromine? On this. Is everybody comfortable with this?
Yes.
Yes.
Okay. So now what we have to do, we have to compare SN1 reaction, reactivity of SN1 reaction. So what we will see here, which carbocation is more stable, right? Am I correct?
Yes.
So when bromine will leave, then we will have carbocation here, right?
Yeah.
Just keep responding, and we will have bromine. If it will leave, then we will have carbocation here. In this case, we are having carbocation. In this case, we will have carbocation here, and in the last case, we are having carbocation at this position, right? Are we good?
Yes.
Okay. So now, can you see this carbon is 1 degree carbon? Means only 1 carbon is attached with it, right? This is a 2 degree carbon. No problem. Tell me. This is a 2 degree carbon. 2 carbon is attached with this carbon. Okay.
Yes.
And this is also How many
Two.
carbon is attached with this? Two carbon are attached with it, right?
Yes.
This wait. This is a carbon. Na? So how many carbon are attached with this carbocation? Tell me. Only one.
Hmm.
Only this carbon is attached with this carbocation, right?
Yes.
And this carbocation, how many carbon are
Hmm.
attached with this?
Hmm.
3 degree, right? Are we good?
Yes.
So from this, you can see, like for example, this positive charge. So this is the alpha carbon, right? We can see there are two ways. I will make you understand. There are two ways. 3 degree carbocation is always stable than 2 degree carbocation is always this carbocation thing is always. This is you can learn and you can just apply. But what is the reason behind it? This carbon, sorry, this carbon is attached with this carbon only. So you can get confused. I'm so sorry. So where were we? So this has two hydrogen, right?
Yes.
So two alpha hydrogen is present.
Yeah.
We have this alpha carbon and this alpha carbon. We have three here, 1, 2, 3, 3 hydrogen, and we have 2 hydrogen here. So we have 5 alpha hydrogen, right?
Yes.
And in this, we have this alpha carbon. We have only 1 hydrogen here. So we have only 1 alpha hydrogen, right? And here, how many alpha hydrogen is present here?
Nine.
How much?
Nice.
9. Good. Who has said the answer? Hello. The answer was
Yes.
correct. So, Sufyan, yes, good. You are correct. Taha, have you understood how many alpha hydrogen is present in this?
No.
9. Okay, good. So, directly we can say that yes, this one. What we can finally say, let's assume it like A, this B, this is C, and this is D. So which one is more stable? Sorry, this reactivity order, the reactivity order of SN1, which one will be the highest in ABCD?
D.
D. Then
D.
B, then A, and then C. Got my point?
Yes.
So since we have compared them with directly with the carbocation, right? Now we will predict with the reactivity of SN2. Kindly note it down first. Kindly do it fast. Done. Sufyan and Taha.
Yes.
Yes.
Done.
No.
Okay. Have you copied?
Yes, sir.
See, this thing, na, carbocation stability is 3 degrees greater than 2 degrees 1 degree. This can be directly applied here also. See, 3 degrees has been the most correct one. Then 2 degree, B, then A and C, right? Without counting of this alpha hydrogen, okay? But in special cases, like for example, A and C, both are 1 degree, right? This one is also 1 degree and this one is also 1 degree. Can you see this?
Yes.
This
Yes,
one
sir.
is also 1 degree. But we can only comment after we have counted alpha hydrogen. Okay? Got my point?
Yes, sir.
So that is why we with the full concepts you can conclude with the correct answer every time. Otherwise, you can also comment on if 3 degrees there, 2 degrees, 1 degree is there, then always this will be the correct option. Okay? Got my point?
Yes.
Okay. So now reactivity of SN2. So in what happens in SN2? The nucleophile attacks from behind, right? Do you remember? Nucleophile attacks
Yes.
from behind. Yeah, we have discussed in today only.
Yes.
This, right? So what you will see, try to understand here, that if nucleophile is, if this carbon is surrounded with very bulkier things, very bulkier ones, then nucleophile will not get a space to attack it from behind. And if they are small like this, so the nucleophile will have enough space to attack on this carbon. Okay. So what we have to check here, steric hindrance around this carbon. Okay. Means nucleophile is getting any space or not to attack on this carbon. Okay. Got my point?
Yes, sir.
So what is the issue here? The issue here is SN, this steric hindrance. Okay. Amna, are you getting this? So let's write some points. Since in SN2 reaction, nucleophile attacks from behind, from behind. Thus, reactivity depends on the number of bulky groups present with carbon. Got it?
So,
Good. So when we will compare, like for example, carbon is attached with CH3, 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 and here we have it is attached with X, which is a leaving group, right? Same. So in which one this steric hindrance is most? This one, the first, second, third, or fourth? H is bigger atom or CH3 compound? What do you think? Amna? H is bigger or CH3 is bigger in size?
CH3.
CH3 is bigger, right? So CH3 is bulkier. So in this one, this nucleophile will attack here very, very properly, and here this nucleophile cannot attack because these are very bulkier groups. These are very bulkier groups. So the attack is not possible here. Okay. So the reaction order will be this. Got my point? So have you understood this? Taha?
Yes, sir.
So the reactivity order is completely opposite with SN1 reaction. So reactivity order here will be 1 degree is greater than 2 degree is greater than 3 degree. Okay. Got my point? This is a 3 degree carbocation. This is a 2 degree carbocation. This is a 1 degree carbocation. Okay. If X will leave